We've all heard some variation of the phrase, you can't make something out of nothing. It's true, but let's talk about why it's true. After all, part of chemistry is taking what we've commonly accepted as the way things are and wondering why they're like that. And we know why we can't make things out of thin air now, but there was a time in history when we didn't. People used to believe that through alchemy, they could create gold out of, well, things that definitely weren't gold. It wasn't until a pair of chemists started questioning why it wasn't working that we adopted the law of conservation of mass and the key to balancing chemical equations. Today, we'll learn what those chemists discovered and how it applies to balancing chemical reactions in this episode of Study Hall Chemistry, presented by Arizona State University and Crash Course. I'm Will Komar. Let's dive in. At its heart, alchemy is the ancient belief that the chemical manipulation of common materials can yield some seriously valuable stuff. Gold, or even an elixir that provides immortality. It involved lots of complicated rituals, weird-looking apparatuses, and secret-coded notes. It wasn't all wizardry, though. Alchemists wanted to prove they could manufacture their own gold with science. They just couldn't, and it wasn't for lack of trying, trust me. Let's watch some test tubes to see how we figured out why alchemy couldn't work. The origin of the law of conservation of mass is credited to Antoine Lavoisier, who proved the concept in the late 1700s in experiments with the consistent help of his wife and laboratory partner, Marie-Anne Paul's Lavoisier. Antoine is widely regarded as the father of chemistry, but we have Marie-Anne to thank for not only translating scientific publications, but also assisting in the experiments proving the law of conservation of mass. The experiments she helped with sought to prove people couldn't create anything from a reaction that wasn't already included in some form at the beginning. They weighed reactants and products to demonstrate that the amount of matter before and after a reaction was the same, regardless of what form it was in. This sounds simple, but it was pretty difficult to prove that it worked for every case, especially with gases that no one could see. It required a lot of money to build lab equipment capable of collecting the measurements they needed, but it paid off, for the most part. The French really didn't like the rich. The experiment results not only validated the Lavoisier's belief in the conservation of mass, but also explained exactly why alchemy was never going to be a success. We can't create something new if we didn't have the building blocks for it to start with. The law of the conservation of mass states that matter isn't created nor destroyed, but rather conserved and just present in a different form. In a chemical reaction, the reactants and the products must both have the same materials in the same amounts. We can't start out with a reaction containing only zinc and oxygen and magically end up with gold, or 3 times the amount of zinc we started with. So when working with reactions, we need to be sure we're following the law and not committing a chemistry crime. The best way to do this is by balancing chemical reactions, which ensures there's the same amount of atoms for each element on both the reactants and product sides. The process sometimes goes really smoothly, but even with years of experience, there are times when chemists make mistakes or get frustrated with the reaction that's given us trouble. Luckily, there are lots of different ways to go about balancing equations, and we'll show you what those are in case one of those works better for you than others. To start, let's say we've been asked to balance a chemical reaction between zinc metal and oxygen gas to produce zinc oxide. First, we write out our initial version of the reaction, being sure to leave enough space between each part where we can write coefficients. Almost forgot. Oxygen is one of the 7 diatomic molecules we covered in the first episode, so this would actually read as O2. We don't need to make the oxygen in zinc oxide diatomic though, since the rule only applies when oxygen is by itself when it's elemental oxygen. Second, we'll write the number of atoms per element. Currently, we have 1 zinc and 2 oxygen atoms in the reactant side, with unknown zinc and unknown oxygen on the product side. For now, we'll say we have 1 each, just to give us something to start with. A helpful way to keep track of our numbers is using a visual approach called the balancing scales method. We draw up a set of scales with one side representing the reactants and the other side representing the product. The number of atoms for each reactant and product goes onto the scale, and we add atoms to one or both sides until they balance out. We know from our scales that in order to make the oxygens equal in our reaction, there needs to be 2 oxygens on the reactant side. So we add a coefficient. We can't add subscripts to equations the way we do with coefficients. As easy as it would be to put a subscript of 2 on the oxygen in zinc oxide, that would be committing a chemistry crime. We'd be making a different kind of compound instead of making more of it. So let's add a coefficient of 2 and recalculate our scales. But now we have 1 zinc in the reactant and 2 in the product. This is really common when balancing. Sometimes we have to unbalance some elements as others become balanced. Don't get too worried if this happens. Much like tidying a room, sometimes it has to get a bit messier before we're done. We'll repeat this cycle of adding coefficients and recalculating our scales until our reaction is cleaned up. Okay, so if we need 2 zincs on the reactant side, we need to add another coefficient. Let's double check. Now we have 2 zincs on both sides and 2 oxygens on both sides. We have equal amounts on both sides, so we're finally balanced. For some simpler reactions like this one, we could also balance them using mental math, without having to draw pictures or write down numbers. But with some of the trickier ones, that's not always possible. In these cases, we can employ another approach, the table method. Let's use it to balance something a little harder. Zinc metal reacting with phosphoric acid to produce zinc phosphate and hydrogen gas in a single displacement. We'll employ the same strategy we did before, but with a few extra steps. First, we'll write out the initial equation. Then we'll draw a table with 2 columns, one for the reactants and one for the products. Within the table, we'll write out the different elements involved in the reaction. In cases like this, it tends to be easier to balance if we leave hydrogen and oxygen for last. Not only because they're both diatomic, but also because they tend to show up in multiple places and can be harder to balance. Another tip that would make things easier is to start with the single elements like zinc. So, if we need 3 zinc atoms on the reactant side, we'll add a coefficient of 3 and recalculate. We'll continue adding coefficients until the values for all our elements match on both sides. In this case, we'll have to remember our rules from the previous episodes regarding subscripts, especially for phosphorus and oxygen on the product side. Since they're hanging out together in the parentheses, they're both multiplied by the subscript of 2. One helpful tidbit: when balancing hydrogen or oxygen, it's best to start with the places where they show up combined with other elements first, and then balance where they're alone. This gets the harder math out of the way and ensures we don't keep going back to rebalance the one that's single every time we change another coefficient. It's kind of the reverse of the rule we use for other elements. Since we've already worked on the combined hydrogen and reactants, let's add a coefficient to the product side, hydrogen. And because we've already added the correct coefficient to the reactant side, oxygen, we have balanced oxygen as well. Let's double check to make sure we're fully balanced with our final equation. Our table helps us confirm that we have indeed followed the law of conservation of mass. Success! There's a couple more hacks that make balancing complicated reactions a little easier. To illustrate, let's use an example of a reaction like this one. We're lucky this time. We have carbonate and hydroxide on both sides of the reaction. These are both polyatomic molecules, charged combinations of atoms that are tough to break apart. Keeping polyatomic groups together, when possible, speeds up our balancing work. We can then say we're starting with 1 carbonate in the reactants and 3 in the products, and 3 hydroxides as reactants with 1 hydroxide in the products. From there, we can balance carbonate by adding a coefficient of 3 to the reactant side. Another tip is to balance the element with the largest number of atoms in the reaction first, not counting oxygen and hydrogen. If we're balancing an equation that needs a large coefficient, it's better to find that out early on. In the case of this reaction, if we take a closer look at lithium, we'll know we need 6 lithium atoms in the products to balance the 6 now on the reactant side. From there, we can easily balance aluminum by adding a coefficient of 2 to its reactant side, and done. Occasionally, we encounter reactions where we need to use a fraction as a coefficient. This happens when we have an odd number of atoms on one side and an even number on the other, often because diatomic elements add that to even numbers. This sounds really frustrating, and believe me, it is, but we can problem solve our way to a solution. Say we are part way through balancing this reaction. Using the table or balancing scale methods, we've come to 6 carbon and 14 hydrogen on each side. But now we have 2 oxygens in the reactants and 19 in the products, and we're stuck. The only way this will balance is if we add the coefficient 19 halves to the diatomic oxygen. If we do that, we're technically balanced now. All our atoms add up to the same amount, but having a fraction there is kind of impossible, so we need to make it a whole number. What we can do is multiply the entire reaction by 2. All our reactants double, and our fraction disappears. Let's check that we still balance. Nailed it! Once we got past the scary exterior, this wasn't too terrible. With practice, this whole process can begin to feel less choppy and more like a known rhythm. And with that, we've covered the basics of balancing reactions. We'll rely on this skill a lot as we continue to master the principles of chemistry. And now that we've explained the importance of the law of conservation of mass, you and I can both agree that alchemy is only a success if you're a wizard. For us normal human folks, our key to chemistry is to balance chemical reactions using visuals, mental math, or tables. Next time on Study Hall Chemistry, we'll talk about how to reliably predict products for each of the various reaction types we discussed. Thanks for watching Study Hall Chemistry, which is produced by Arizona State University and the Crash Course team at Complexity. If you like this video and want to keep learning with us here in Study Hall, be sure to subscribe. You can learn more about ASU and the videos produced by Crash Course in the links in the description. See y'all next time.